Contrast, resistor, inductor, and capacitor high frequency models. We'll just talk about it briefly. And then from there, I'll probably move into some filtering. And if we get lucky, we'll get to the common mode choke filters. But we'll see. So right now, this is Bode plots. So for Bode plots, there's a couple things to know. First, we assume that we're going to have everything in terms of S. Sometimes they do it with J omega. These are frequency domain plots. Do y'all follow me on this? Probably the easiest one to do is don't even worry about impedance or anything like that. Worry about a transfer function. So if we have H of S, and this is common, and this is how you construct the function too, just for the record. If you have H of S, you always start with some scaling factor K. This is arbitrary. You don't know what that is. Then after that, when we're dealing with Bode plots, we're talking about poles and zeros, if you'll remember. Poles are values of S that will make that function go to infinity. Zeros are values of S that make this function go to zero. Makes sense, right? So the poles are always located in the denominator. And they'll be like S. Now, a lot of times in your books, you'll see minus P1. I just like to call it S plus A. I'm doing this because A is an arbitrary constant. When I put S minus P and stuff like this, the negative signs tend to mess people up. This is the way it'll appear most commonly in functional form. S plus B type stuff. These are poles. The values of the poles would be at S equals minus A and S equals minus B. Do y'all follow that? They cause the value of this function to be infinite. Just think about it. If S, regardless of what B is, as long as A and B are the same, if S is minus A, then this is zero, right? 1 over 0 is infinity. It's called a pole. The thing looks like it's a pole that goes to heaven. Goes to infinity. Y'all with me? These are zeros. And I just chose this, S plus C, S plus D. That's on top. Now how this looks all depends on the values when we plot it of A, B, C, and D. So we're going to make a few assumptions, and this is only on me. I'm going to say A is going to be less than C, is going to be less than B, is going to be less than D. Then I'm going to say that S is really complex, but we're just going to have S equal J omega. This is common. We ignore sigma. So this is really something where the S is just the complex portion of the complex frequency. It's just the J omega term. And then what we usually do when we talk about this, when we talk about Bode plots, here we plot the log of either omega or S, log magnitude. Actually, I'm just going to put log of omega here. Sometimes they put magnitude of S. Sometimes it's log of F on this axis, right here. And here, we plot 20 times the log, that's a base 10 log, of the actual function H of S when S becomes J omega. Is everybody clear on that? Now you all saw this, right, before? All right, when you do this, what do you usually, if I'm going to do this, do you remember the trick, anybody? There's a couple of ways to do this. What's generally done is, I'm going to just digress for 1 second. If you have any plot, right, where I have K over, and then I'm going to have S over A plus 1. When you look at this, and I take 20 times the log of this, right here, what do you know? When S is a very small value, right, you really have 1 downstairs, don't you, class? And then when S is equal to 1, you have really the square root of 2 in magnitude, don't you? But if you were to plot just that versus A, For values, this would be of S or of omega, j omega. I'm going to use S here, to the magnitude of S. For values less than this plot here would just be 20 times the log of K, isn't it? It would stay there until I hit until I hit A. Do y'all remember doing this class? Now, when this all of a sudden goes to 1, it'll start coming down at a rate of minus 20 dB per decade. This is kind of important. Y'all remember that? That'd be log. Actually, I put S there, it'd be log of S. So how do you know that? It's a good question. And I want to answer that question. I want you to look here. When we're right here, actually the real curve is a little less than this. This will be 3 dB difference, and here's why. When we're at S equals A, actually S would be J A, right? It's when J omega equals S. So this would be J A over A, or just J plus 1, wouldn't it, class? What is the magnitude of 1 plus J? Magnitude. It's square root of 2, isn't it? So when we plot this, and it would be log of the magnitude of this, we would have at this point right here, 1 over, and this would be square root of 2, and it would be 20 times log of that right at this point. Well, this is exactly 3 dB less than that point here, this flat point. Do y'all remember that? That's the reason they call it a 3 dB point, or the 3 dB point. I don't know, do you remember that terminology? That's the reason, because that's where the actual change in value is 3 dB from the prior values at lower frequencies. And it's coming down at a rate of 20 dB per decade. Now, some people don't understand this. The reason is, we're assuming this transfer function is a ratio of voltages or currents. A typical transfer function would be something like V out over V in. Y'all with me? Transfer function, relationship between output and input. Well, the reason we say 20 dB per decade is because if we look at this value and we go over 1 decade of change of frequencies. So if we start at S over A equals 1, I would have K, or the square root of 2 would be here, or it would really be here, wouldn't it, class? We assume at that point starts breaking. Then if S over A is 10, we have 1 over 10. Well, the log of 10 is what? 1 times 20 would be a factor of minus 20 below. Do you all follow me on that, class? How many do? All right, so the 20 dB per decade would be for something like this. If this was squared, it would be 40 dB per decade. Do y'all remember that? And we could go on. If it was cubed, it would be 60 dB per decade. But you need to understand how they get the dB per decade, because a decade is an order of magnitude, or a factor of 10, right? So 1 to 10 is a decade, 10 to 100, and so forth. 20 dB per decade would be that. Back to this thing now. So what I have to do, and here's where I slow down, make sure I make my point. That you've had. You don't just brute force this function. What you want to do is have all the coefficients here inside these S plus A, S plus B, be S divided by something plus 1. Do y'all follow me on that, class? This is real important. I mean, you can plot it a different way, but this is the way you should go. So I leave K alone. Now, if I want to divide by C here, right? Divide the inside by C, I have to take C outside. And then I have S over C plus 1 here. Y'all follow me? Right here, that's the first part. I'm going to slow down and try to make absolutely sure you see what I'm doing. Now I'm going to take a D out of this one. So I take D here, and then I have S over D plus 1 here. Then I divide downstairs, and I take an A out of here. I take a B out of this one. And now what I'm going to do, that's still the transfer function, I'm going to group all the constants. Do y'all follow me? Now the C and D were upstairs, the A and B were downstairs, so this looks like K times quantity C times D over A, B, and then it's times S over C plus 1 times S over D plus 1 over S over A plus 1 S over B plus 1. And then we're going to take 20 times the log of that. Y'all follow me? How many remember doing that when you did the log plot? Nobody? You remember? How many do? Honestly, raise your hands. I saw heads nod. This always troubles me. I don't know. Kind of, sort of. The reason I did this is you see how it's real easy to see why these are just 1 when S is less than these values, like D or C or B or A. Y'all follow me on that? When it's 1 plus something small, you know it's basically 1, and it's not a problem. Therefore, all these, this is where all the constants are wrapped up. This is my point. It's real important to do this, and I want to do the homework too this way. So when I come over here, if that's the function, I have 20 times the log base 10 of this. K, C, times D over A, B. That's always going to be there. Y'all follow me? I'm taking 20 times the log of that function. Guys, you with me? Everybody? Now, what am I going to do? The top part here is additive. Plus 20 times the log here of magnitude 1 plus S over C plus 20 times the log base 10 of 1 plus S over D. Down here, when I take 20 times the log of these will be minus, won't they? I just want to make sure everybody understands this. If you have 20 times the log of A over B, that's 20 times log of A minus 20 times log of B. Everybody follow me on that? Y'all remember this? I'm not trying to bore you, I'm just trying to make absolutely certain I don't have uncertainty in my class about Bodhi plot. Do you all remember that? All right. Now, here is what that 20 times the log of my fictitious HS looks like. And here's how you do a plot like that. Hear me. Now, sometimes you can't, but I'll get into it. That's if you have just a 1 over S term. If this had a 1 over S term, then you can't do that, what I'm about to show. But the way you normally do this is you start with the constant and you evaluate this constant. The 20 log of K, C, D, A, B. That's a value, it'll always be there. Y'all follow me? That's what it is when you're less than, and I'll put them up there. I've got A, then I got C, then I got B, and then I have D. I don't know how these are, but down here, the value right here is 20 times the log base 10 of magnitude K, C, D over A, B. You don't know what that is, but it's there until you hit the first term right there, which happens to be a pole, right? Y'all follow me on that? Now, when you get to A in this plot, it starts going down at 20 dB per decade. Y'all with me? You just draw straight line plots to approximate this. And Dr. Hung probably does this slightly different, but this in essence is everything you need to know about a Bodhi plot. Both plotting it and then constructing a function to represent something. So please understand this is both for synthesis and analysis. All right, now it starts going down by 20 dB per decade until I hit C. You all agree with that? What happens at C? Well, I said C was greater than A, but it's less than B. It's the next frequency up the chain, right? So what happens? Well, at C, where is C? C is a
0.
What?
0.
A 0, so now what? It starts increasing at 20 dB per decade, right? But it was already decreasing at 20, right, per decade, so now it's just flat, isn't it, class? Y'all with me? It was decreasing, then it tried increasing at 20, it canceled the effect of decreasing. Real important you see that. Got that? Now what happens next? I said the next thing you hit is B, which is a pole. It starts at 20 dB per decade again, right? Until I hit D, and then what happens? Where's D?
It's a 0 or
And then it will what?
flatten out again.
Flatten out, correct? Because then you start, so it looks like this. Now, if I had to give that a name, it would look like a weird low-pass filter. Be honest with you. It's passing where the value's maximum at lower frequencies, correct, class? Y'all see how I could change those values, and I can have something different. Y'all with me on this? I can change these values, and I can have this thing basically, I could have it going up and then level, right? And then come in, if you all with me on this? So you can play a game about A, B, C, D to get anything you want, from a notch filter, low pass, to a high pass filter. And we can keep on playing games here, but that's in essence what I wanted you to get from this. Now for the problem I gave you, I'm gonna erase this and just talk my way through it. You're gonna get something like this. Dr. Whitmore's book does not have a lot of stuff where you do synthesis or analysis of Bode plots, but he does show you, in essence, Bode plotting. But you're engineers, and I'll tell you one thing, in the real world, in engineering, most of the time when they do any kind of frequency analysis where they take all these measurements, they'll get all these, they'll get plots. Those are exact plots. Then usually they'll try to represent them as first pole, second pole, represent them as Bode's because they're so much easier to do engineering with. Not always, but a lot. So in the problem I gave you, I had, I'm looking here, just gonna grab one. Did you have a question? Okay, good. It was this. This is versus F, doesn't matter what it is. It's a logarithmic scale, and this is just shown as 100 ohms. It's indicating that 20 times the log, the 100 ohms would be at that point, but it's listed as 100 ohms. This is right out of the book. And that's at zero, it's flat, 0 dB per decade. Here's the first cut frequency, and this is F, not omega. F is equal to 1.592 times 10 to the third, right? And that's hertz. And then it's coming down to 20 dB per decade. And then it hits here. That's the center frequency, and 5.029 times 10 to the 6, that's way up there, hertz. It starts going up at 20 dB per decade, right? Correct, class? All right, so now we're gonna go through this. And I want you to understand something. The way I'm gonna do this, all right? There's probably more than one way to do this. First, that's a resistor. All right, it's a resistor of 100 ohms. I already gave you the low frequency cut and the resonant frequency for a resistor. I put them on the board last time. But I'm gonna do this based on a Bode plot, okay? So when we do this, the first thing I note, this is an F. So I'm gonna go ahead and get omega here. Omega would be 2 pi times this F low, whatever it is. And I wish I could do that in my head. Can you just give that to me, anyone? I want to put it down here so you see how I would do it. I usually do these things in terms of omega, or really fast. So you understand exactly what I'm doing.
It's about 10,000.
10,000?
Mm-hmm.
Anybody confirm that?
Yeah.
All right, so it's 10 to the 4th and that would be radians per second. What about this one? That would be omega low, and this is omega self-resonance. Just 2 pi times that.
(31.6 times 10 to the 6).
Is that right, class?
I got 30, oh yeah, 3.1, 10 to the 7, yeah.
Well, this is 5 times 10 to the 6, so times 2 would be really 10 to the 7th, right? 10 times 10 to the 6th, or 10 to the 7th times pi. So yeah, 31.4?
5.
Th-
Six.
31,
6.
pardon?
31.6.
0.6.
Yeah, we're just gonna keep counting.
Is that right?
Yes.
About.
Mm-hmm.
I'm just calling it rough. All right, now, when you do this, the way you might have been taught, you know, for this thing, Z impedance, right? Remember what I said, that all the constants would come out in front, right? But what I'm going to do first is just show you the general function before the constants. So it's K, and now I take a look at this. I know I have a pole down here. I'll just show you I'm up here. So I'm going to divide by S plus A. That would be this pole right here. That's the low frequency, right? And then I have what? I have a 0 here, don't I? And it's going to increase at not flat at just 20 dB, but at 40. Correct, class? Y'all follow me what I'm saying? So that means here is what? S plus whatever that B is squared, right? I'm not done with this, but I just want to make sure you see what's going on. Yeah.
How do you know that's squared? How did you get
All right,
that?
here's how I did. See how this is going down at 20 dB per decade? If it was a single pole, it would be
It would just flat.
So that would be just S plus B.
Cool.
But because it's going up at an additional 20 dB, I square it. Y'all follow me on why that's true, right? If it was going up at 40 dB per decade, what would I do?
To the third.
It would be S plus B to the third. Now, the next thing I'm going to do is get the constants out. Y'all follow me? Because I got the poles there, don't I? So this is the way I do it. So I would say this would be equal to K, all right? Now, downstairs I know I'm going to have an A times S over A plus 1. Upstairs I've got a B squared, right? So actually I'm going to take a B squared out here, and then I have S over B plus 1 squared. Isn't that right, class? Y'all follow me? I want to make sure you see what I've done. Now, when I do this, and I take 20 times the log of that function, of this, I'll just call it magnitude of Z here, this is going to be 20 times the log here of K B squared over A, all right? Then it's going to be minus 20 times the log here of the magnitude of S over A plus 1. And then it's going to be plus 40 times the log of the magnitude S over B plus 1. And that is the logarithmic plot. Do y'all follow me? I don't know if you did it. Did anybody do it this way? How did Dr. Hung teach you to do this? Or did you use MATLAB to do it? You can do it several ways. You can just take the formulas I gave you and get it. That'll do too. But you should ultimately plot it and make sure you get that, just to make sure your functional form is correct. But you all see what I'm doing here, class. All right, what's my next step? Take a guess.
Can I ask you a question real quick?
Yeah.
When you take the B squared out of S plus B, I'm confused as to how that math is working out.
All right, let's do it this way. Follow me. I'm going to take a B here, all right, squared out of this, right? Let me do it this way. Let me actually do this. We'll see it. I'll take a B out of here, all right? So I have a S over B plus 1, right? Still squared? Follow me? I just factored a b out of that. I have s over b plus 1 remaining, right? Now that's squared, so wouldn't that be b squared over s over b plus 1 squared?
Yes.
Okay? Just so you, there's no dumb questions here. Believe me, there's things that just don't click sometimes. So I come over here. What do I know for a fact? Right?
Yep.
So that means all this right here is 100. Y'all follow me on that? How many see that? The reason is it's I mean, this should be, technically, this should be 20 times the log of the constants, and it should be about, they saved us that, they just said it's 100 ohms, okay? So that means the first thing I have is K, I'm sorry, I have K, right? B squared over A equal 100, right? Y'all agree with that? I'm putting it down, I'm trying to make sense of this, because this, folks, I promise you, what I'm showing you, I always thought people knew, but I think they were taught how to plot a function and not how to analyze and create a function. I mean this, so I'm showing you how it's usually done if you're synthesizing something. Now, what else do I know? Don't I know this low frequency pole, right? Correct, class? That's this, isn't it? So I know A is equal to 10 to the 4th, and that's radians. What about B? B is 31.6 times 10 to the 6th, correct? Isn't that right? Y'all follow me on this? So what does that do? It allows us to get the actual value of K for this function. Y'all follow me? So now I say 100, I'll just rewrite this so you can see it. I had K times B squared over A equals 100, or A times 100, somebody help me out here, over B squared is equal to K, and that equals what? That's 10 to the 4th, 10 to the 6th, right? Over, and B is 31.6 times 10 to the 6th squared, so that gets rid of one of those 10 to the 6th, so it's what? 1 over 31.6 squared times 10 to the 6th, whatever that is. But could you give me that value? I can't do that.
1 times 9 to the power 9. I mean 1 times 10 to the power 9.
I can confirm.
All right, 10 to the minus 9. Y'all follow me on that?
It would be 1 to the minus 9.
10 to the minus 9 is 1 times 10 to the minus 9.
Yeah, you're right.
It's all right. Especially if you're up late. All of a sudden, things like that just... Are y'all with me on this? But that's not the value of this, is it? Wait a second. That's not the value of this, is it?
No.
What's that?
100.
Isn't it, class? All right, so this is 100 in there, and if you're doing it, that means this, I'm just showing you how to get the value of K. So that means this functional form right here, if you wanted it in this form, please just listen for a second, because I know people do. This is the form I see most readily. But I'll see people just put K in here as 100. Y'all follow me on that? They'll just do that instinctively. It's not the value. That's the value of K in this equation. Y'all follow me here, class? Because at low frequency, what happens? At very low frequencies, S going to 0, then K B squared over A is the value of 100, isn't it, class? It's not this K, so you have to do it that way. Now, when I get it down to this part, the reason I like this part is this is 100. And that is easy, because now you see that's the 100, and there are the coefficients there. Y'all follow? I mean, I'm dividing S over A. Usually in the Bode plots and signals and systems, or I should say in the actual transfer functions, it's usually S plus A, S plus B, isn't it? It's not S over something. Do y'all remember that? And that's the reason I'm spending time on this, because people, when they do synthesis and analysis, they get confused with this constant all the time and how to get that particular constant in the plot if they're doing it like that. Because I'm just telling you it happens, okay? All right, I did that for a reason. Now, I asked you to create, if you put the inductor, or if you put a capacitor, use the resistor and use the RC model for that, it was very straightforward to get both C, right? Because 1 over 2 pi RC was the low frequency cutoff, right, of hertz. And then the high frequency cutoff was 1 over 2 pi square root of L times C was the high frequency cutoff, right? And you had C. You get that from, because you knew R. You all agree with that? Okay. Just wanted to go through this. All right, now, inductors, and then contrast the models. Let me ask you one thing before I move on. If you were to develop a model to approximate this, I want you to tell me, how'd you do it in terms of the transfer function? Say my H of S here, this is going to be a log scale, or make it omega, and it's log of omega, actually. And then up here, really it'll be an H of S. And I'm going to have this function. I'll put it 1. This would be 100, but this is a logarithmic scale, so this would be 10. And this is going to be just keeps going down. This is going to be minus 20 dB per decade. How would you create a function to get that?
Add K and go through and find the zeros
Put
and
K
poles.
first. You don't know. Just act like you don't know. All right. Now after that, I know what this thing's coming in. Looks like it doesn't have a cut point. It just comes in continually. It's that rate. Y'all follow me? So that is a pole with no offset. It's a 1 over S term. So this would be just S. Do y'all follow me? That is the form of a capacitor itself. It has a 1 over J omega or 1 over SC type form. It's coming in. As the frequency goes to 0, the impedance goes to infinity. Y'all with me on that? Just trying to give you an idea, something to think about when you're plotting this. So now I've got 1 over S. Now,
for positive slopes like that, is it?
that's a 0 particle. You're absolutely.
That's right.
I'm sorry. I reversed this. This should be an S up here.
Okay,
I'm
I'm
so
not
sorry.
tripping.
That is absolutely right. That was my mistake. This is coming up. So, by the way, I tried to make it here. It went 2 orders of magnitude, 40 dB. That means that's 20 dB per decade. So it's S to a single power, right? Now, at that point right here, what happens? That's a pole, right? And it starts going down but now it's going down at 20 dB per decade. It was going up. This was a positive 20 dB per decade, right? And now it's going down, so what?
2 poles.
It would be S plus A squared, that would be the pole, I'm just putting the general form, do y'all agree with that? Now, after that, if you're doing this, and I'm gonna do it the way I like to do it, here, I'm gonna take K over A squared, I'm taking an A squared out of there, and then I have S over A plus 1 squared, right? And now I say, well, when I do this, I have 20 times the log of h of s here would be equal to 20 times the log of k over a squared plus 20 times the log of magnitude s here minus 40 times the log of magnitude of s over a plus 1 here. Isn't that the formula? I want to make sure, I just want to finish this. I'm not trying to bore you, but I'm trying to make sure you see this, because there's certain things, I'm glad I made that mistake. The first thing you got to do is what? You know it's 0 dB here, right? And you'll notice this one can't be ignored. Y'all see that? But I chose one value, it's kind of nice. What is it? When S is magnitude is 1, what's the log of 1? 0, isn't it? Log of 0 is minus infinity. Log of 1 is 0, right? Which makes that nice. So over here, when we have 0 dB, we have 20 times the log of magnitude k over a squared. This term goes away, this term isn't on yet. Y'all follow me? They still have log 1 there? So it makes it nice because that means if I have 0 dB to the 10th power, I have simply what? 1 equals k over a squared. Y'all follow me? Class, I'm just trying to really help you here. I know I'm maybe boring you, but I'm really trying to help you. So now, the next thing I have, I've got the relationship of k and a. Now I need a. Luckily I plotted an omega. So a over here is what? Just 100, isn't it, class? Y'all follow me? Because I plotted versus omega. S is j omega. You agree with me? So over here now, if that's 100, I can say 1 is equal to k over 100 squared, or 10 to the 4th, or k is equal to 10 to the 4th. And therefore, this function or that function, you have the values for that models that. Y'all with me? Now, here's what I'm going to warn you about. See, this is as easy as it looks. I'll give you something like this, and you watch and see. If I don't get about 1/4 of the class that flubs this up because of something they didn't quite understand. So please understand that, okay? I'll give you a promise. Now we contrast everything. Wasted a lot. I didn't waste, but I spent a lot of time on this because I know that when you do controls, it's really for analysis and to see if systems are stable or unstable. Do you still do Rouch-Hurwitz or not?
Yeah, we did that.
Oh, gosh. Computers are usually used to analyze stability these days. But it's an old way to find out if a circuit's stable, if a system's stable. And one of the things, too, is this. You're focused on complex planes and where the poles are located, 99% of the time when you're doing control work. I'd say that. That's probably fair. Most of the time in the real world, when you're doing antenna design, you're trying to make sure you have the right functional form for the impedance of the antenna, and you understand it. Now, you can modify certain things in design, but it's really understanding antenna designs in terms of a Bode plot, the impedance of the antenna in terms of Bode plot. Now, we go through a contrast. So if we have a resistor, the high frequency model, we always start with the resistance, right? Then you put a parasitic capacitor around it, and then you put inductance that represents the lead. And this is your model for a resistor. You all with me? If we take a look at the model for a capacitor, and this is the high frequency model, you start with the element. This particular model is not appropriate for an electrolytic capacitor because they have a lot of leakage, so you would see a leakage resistor right inside of here. Like literally it would be a parallel one. But normally when we deal with mica capacitors or low loss capacitors, you'll have this. You'll have a resistance here that has to do with the wire. And this is R, I guess it's parasitic. And it has to do with the lead length. And then you would have an inductance, L. And this is the general, and this is a parasitic inductance as well. That would be for a capacitor. Do y'all remember that? The capacitance is given. And the reason is, if you look here, isn't the capacitance of this system, or the impedance of this system between these two terminals when the frequency is 0, isn't it infinite? So there is no leakage resistance. With an electrolytic, they put a leakage resistance here. And that model is a little more complicated, and that's only for electrolytics, really. Finally, for an inductor, I didn't do this. This will be the high frequency model for an inductor. You always start with an inductor. Actually, I did part of this. That's just, when you think of inductors yourself, I always think about a lot of wire that's wound close together. Now, the truth is they don't have to be wound on a cord. If you have a serpentine system like this, it will have inductance too. There's a lot of ways where you get inductance between, self-inductance of a line. You don't have to coil, but coils are the most common. Coils are used, just think of transformers when you think of inductors. That's what you're doing. When you have an inductor, because of the amount of wire, you're always going to have a resistance internal to the wire. It's a parasitic resistance you can't get rid of. It's associated with the gauge of the wire. The inductance has to do with the number of turns and radius of the turns, each turn. Then across both of these, you're going to have a capacitance, like so. And here, that's a parasitic capacitance. Anything that's unwanted, I put a sub P on. When I teach my EMC course, I didn't get to teach it this year, I didn't have enough students, but the electromagnetic compatibility and interference course teaches you how to, if you have interference and stuff like this, how to get rid of it and how to really understand high frequency components. These are just basic components, but I mean other components, because if you don't thoroughly understand these, when you get up around a gigahertz or better, your designs just go to pot. And I told you about my antenna design for the problem with the solder ball. Things like that fall to the floor. Now this one itself, we can show you I can develop the model and we can get it, but this is how inductor models almost always look. At very low frequencies, this capacitor is an open circuit. But instead of having 0 resistance, because there's a DC resistance to that wire, there will be some finite but very low resistance. So if you looked at this, and this would be 20 times the log of the actual impedance of that inductor versus omega here, versus omega, actually I can put it versus F here, because Wentworth's book will do F, and this would be log of F here. You will get something that's very, very low impedance here, and this is going to be something associated with just R of the wire, to be the DC. Then there'll come a point and it'll start going up at plus 20 dB per decade. All right, now what that is, forget this capacitor. If you just have an inductor and a resistor, I want you to just think about this. When all of a sudden the inductive reactance is equal to the resistance, you all see the inductive reactance will start dominating after that frequency. That's how you get the first breakpoint, and I'll get to that in a second. Then it'll keep going up at 20 dB per decade until this capacitive reactance starts becoming equal to these two. Y'all, really the inductive reactance. Do y'all remember when you have an inductor capacitor in parallel, resonance happens when the inductive reactance equals the capacitive reactance. Do y'all remember that? And the phase of the currents are exactly, one is 90 degrees ahead, the other is 90 degrees behind the voltage. The net effect is no current passes when you're at resonance. Do y'all remember that for parallel circuits? The impedance goes to infinity. And what it really does is start coming down at minus 20 dB per decade from that point on. And it'll keep going like that. And that's the actual profile of the impedance versus frequency for an inductor. Now, you'll see this, it's about what? It looks like, I mean, for this one, it looks like the inverse almost of the capacitor, doesn't it? And if you think about it, inductive reactance is SL, or J omega L, and capacitive reactance is 1 over J omega C. It makes intuitive sense. Now, down here, this low frequency, and he doesn't talk about that, that point, and this is not quite exact, when you put really SL equal to R, or S right here is L over R, and S is really 2 pi times F, you get this. The low frequency pole is simply R over 2 pi, this would be F low right here. And that's right here. This, most of the time, you don't even worry about. You just worry about this point, and this is at self-resonance. And this F self-resonance here is equal to 1 over 2 pi square root of L C parasitic. Now, the reason I want to just comment on there before you go is this. Hear me. Right here. You know how I talked about resistance of wire is a function of frequency, right? Well, as you're changing frequency, that resistance is changing. What happens is the DC resistance down here is different than the DC resistance at this point. So these things have like this, if you actually get raw measurements. And the point right here isn't as sharp and crisp as you'd expect. Just telling you that is because the actual AC resistance of the wire is increasing as frequency goes up. All right. I'll get that back to you by Monday. And I'm going to give you some homework relating to this voting plot. And, okay.